All right, it's time to learn how to handle Newton's second law when an object is on a ramp or an incline, such as this car rolling without its engine on, just rolling freely down the ramp. To begin with, you want to, like all cases with Newton's second law, you want to identify the forces that are present. So take a look at this diagram. Can you see the forces? You should have identified hopefully two of them. A gravity force pointing straight down and a normal force perpendicular to the surface that causes it pointing out this way. Technically there are four normal forces, one from each tire, but we're only going to treat it as a single normal force and pointing off in this direction, and this force is mg pointing straight down. Alright, next we need to think about the direction of the acceleration, because we need to choose a direction which we shall call positive, and the rule for choosing the positive direction is to choose a direction positive consistent with the acceleration. And we know the acceleration is going to go down the ramp, and therefore that's the direction we'll choose for our positive direction. So we will imagine an axis that runs along this way, like this. Oops, let's go to green, maybe keep it different than our forces. Here we go. We'll imagine an axis that runs this way. That'll be our x-axis. And then we'll imagine a second axis that runs this way. This will be our y-axis. So we've taken our regular Cartesian coordinate system and we have tilted it so that the x and y axes are rotated a little bit. That's all right. We get to do that. We invented these axes to begin with. We get to do what we want with them. And this is the axis that works nicest for our situation. So this direction shall be considered positive. Anything in this direction is positive. Anything in this direction is negative. Look at our two forces that we have. Our normal force runs along the y-axis. It's neither positive or negative. In fact, there is no acceleration along this axis. This is the zero acceleration axis. We don't expect the car to be accelerating up into the sky or down into the ramp. So we expect that there's no acceleration in this direction, and all the acceleration runs this way. The gravity force, on the other hand, is a little trickier. The gravity force is not really along the x-axis, but it's not along the y-axis either. So we need to do something with this gravity force. As it currently stands, it's not really of any use to us. So let's see if we can do something with this gravity force. What we're going to do is try to re-represent the gravity force with two vectors. Do you agree that the gravity force could be represented as this vector plus that vector? Yes. Could it be represented as this vector plus this vector plus this vector? Yes. In fact, there's an infinite number of vectors we could represent the gravity force with, but we're going to choose two very special ones. We're going to choose one that runs along this axis, along the y-axis. Stop it right there. And we're going to choose a second one that runs parallel to the x-axis. These two vectors that I have just drawn are equivalent to mg. And so rather than using the gravity vector itself, that gravity force vector, we're going to use these two and replace the gravity force vector with those two vectors. So let's see, if this one has a value of mg, what value should we use for this one and that one? Well, if you look at the triangle, clearly this hypotenuse is going to be longer than the other two. we need to do a little bit of geometry to see how big these other two vectors are. This geometry is not too hard to understand. It's going to be related to the angle of the ramp itself. In fact, I'm going to assert, and then in a moment I shall prove, that this little angle right here is the same as this angle, which we'll call theta right here. We can even give it a number. Let's call it 30 degrees, just to use a nice friendly number. Let's see if we can show that this angle here is the same as that 30-degree angle there. If we take a line and drop it down along the MG here like this, this line has to form a right angle right here because gravity goes straight down. This is a horizontal reference line. This is a 90-degree angle right here, right here. If this is 30 and this is 90, this angle right here would be 60. And if this is 60 right here, and this is a right angle, this angle here must be 30 degrees. The same 30 that we had over here. And this will always be the case. The gravity vector will form an angle with the perpendicular to the plane vector, which is 30 degrees, exactly the same as the ramp. So with this hypotenuse equaling mg, and this side forming a right triangle, let's see if we can determine the size of each of these two component vectors. You probably recall from trig that the definition of cosine is cosine of any angle is equal to, let's keep it general here, cosine of any angle theta is equal to adjacent over hypotenuse, ADJ over HYP, and if we look at this side right here, this side is adjacent to the 30-degree angle. So if I'm trying to describe this side right here, it's the adjacent side. My hypotenuse is equal to mg, so I can replace the hypotenuse with mg, the gravity force. This is, after all, a force triangle that we're looking at. And if I solve for the adjacent side, I get that the adjacent side, multiplying both sides by mg, the adjacent side is equal to mg, the hypotenuse, if I multiply both sides by mg, times the cosine of the angle of the ramp. So this adjacent side will equal mg cos theta, and our opposite side, opposite to the 30-degree angle, will equal mg sine theta by a similar argument. The sine of any angle is defined as the opposite over hypotenuse if it's a right triangle. Our opposite side is what we're looking for. Our hypotenuse is mg. And if we solve for the opposite by multiplying both sides by mg, we get our opposite side is equal to mg sine theta. Now that we have re-represented our mg as being the sum of mg cos plus mg sine, we're ready to begin analyzing the motion. And we're going to look at this in terms of both x and y. In the x direction, we can write F equals ma this way. And in the y direction, we can write F equals ma this way. Let's deal with the x direction first. Remembering that everything that's pointing down the ramp is positive, we're looking for any x forces. Well, this normal force is a y force, positive. this mg cos theta is a y force, negative, and the mg sine theta is the only x force we have. So it is indeed the net force. So when we're trying to describe the net force, it's simply mg sine theta. So our Newton's second law looks like this. Mg sine theta, the only force in the x direction, equals ma. From here, we can solve for the acceleration. Let's say that's our goal. The m's will cancel, since there's an m in every term. And so you can see that the acceleration can be calculated by multiplying g, which is 9.8, times the sine of theta. Theta, our angle, is 30 degrees, sine of 30. And if you type that into your calculator, you will discover that A is equal to 4.9 meters per second squared. And that's the rate of acceleration down the ramp of the car. Let's take a look at what we can learn on the y side. In the y direction, since there is no acceleration going this way, all the accelerations in the x world, we can say that our acceleration is equal to 0. So this whole right side of the equation is equal to 0. And in the y direction we have two forces, a positive normal force, let's write it down as a positive, and a negative mg cos theta. Let's write that down as negative mg cos theta. And so by studying the y side of the equation, we can learn exactly how big the normal force is. That normal force has to be exactly equal to the mass times 9.8 times the cosine of our angle, 30 degrees. Okay, so how do you attack any problem with ramps? First of all, tilt your coordinate system so that you have one axis that's aligned with the acceleration, one axis that's anti-aligned with the acceleration. Your normal force will always fall right upon your y-axis. Your gravity force will run straight down. It will be necessary to break up the gravity force into two components. This one will always be mg cos, and this one will always be mg sine. And then this force will be involved in the acceleration. It is possible that that force is not the only force involved with the acceleration. There could potentially be like a friction force, and if that were the case, your net force here would become a little bit more complex. This net force would include the positive mg sine theta running down the ramp, but it would also have to include a negative friction force running up the ramp. So that could happen. Those are the essential elements of how to handle a tilted ramp situation. Any force that doesn't conform to the x or y axis needs to be broken up into some components so that it does conform to that axis. Very good. You have all the essentials that you need to solve any problem with ramps. No matter what other complications that may follow, you can be sure of these ideas. They will hold true. Good luck.